Hello to everyone. Hello to everyone who participated in International Conference of Transport Infrastructure, Territory Development and Sustainability. My name is Hadi Davardust and I'm going to present our study about system modeling in solving mineral complex logistic problems with the analogic environment. The study that we had done, we are going to start it with the introduction. Currently, the national program in Russia, which it is the digital economy of the Russian Federation, is one of the most important factor in the growth of almost all parts of the country's economy. The most important parts of almost any multimodal transport system are the terminals that connect and balance the flows of goods moving along different parts of the transport network at the same time. The goal of our study is to find out how well logistics problems in the mineral complex can be solved by using system modeling techniques on the case of the St. Petersburg oil terminal. We tried to solve this modeling by agent-based and discrete event modeling, which in further we are going to talk about them with ABM and DEM methods in abbreviation. The relevance of the work. The northwestern region of Russia ranks second in terms of providing the main cargo flows of the country. That region has a distinct geographical location, borders to European Union countries, and is accessible to the largest European ports. St. Petersburg Oil Terminal, which we are going to talk about it in POT, because it is in Russian, it is named Peterbursky Oil Terminal. It is one of the largest Russian oil product transshipment terminals in the Baltic region, and it's one of the modern and specialized transshipment complex that is a part of the great port of St. Petersburg. The general information about the region is depicted as follows in this table. The parameters and the values are depicted. The number of the terminals are considered as 30, and the throughput is considered as 341,000 kilotons per year, and the number of piers was considered 97, and the loading capacity and the tank farm capacity is as follows. Okay, turning to the simulation model development. The receipt of petroleum products is carried out by three modes of transport. Up to 10,000 tons per day at three river berths, PNT1, PNT2, and PNT3. Vessels with a dead weight not exceeding 5,000 tons can arrive at these berths per day. The vessel's unloading time of 5,000 tons takes an average of approximately 18 hours. At 5 automatic discharge points, up to 3,000 tons per day. The discharge time of the tanker truck is approximately 3 hours. Each day, 5 oil product reception racks can accommodate 108 tank cars. The average service time of the railway train averages approximately 9 hours. In further, petroleum products are shipped in two ways, by sea vessels and by trucks. 4 sea berths, PNT3 and PNT4, for tankers carrying up to 100,000 tons day. On average, 35,000 tons of oil products are shipped every 14 hours intensively of arrivals per day, 1 to 2 ships. Berths 112A, 112B, up to 40,000 tons on average, 16,000 tons per 6 hours. Intensity of arrivals per day is 2 ships. At the maximum monthly capacity of 5,000 tons at 3 automobile loading points, the loading time is 42 to 50 minutes. Turning to the simulation results, the indicator and the value is given as in this table. As you can see, the simulation time accepted volume of oil total volume of oil shipped, loading ratio of posts, average QE length, average waiting time, average service time, throughput, idle time factor, and the number of transport units proceeded are depicted as these follows with their all ratios, and the numbers are depicted respectively. The computational experiment. In order to find out the different factors affect performance, a complete factor experiment was used to study the model, and the first stage of the planning experiment for obtaining a linear model consists of varying the factors at two levels. The regression equation that was found looks like a first degree polynomial that we are going to tell then this regression equation is called an FDP model. Here you can see the equation which it is from the first degree polynomial. The computational experiment. As you can see here we have the matrix which x0, x1, x2, x3 and x4 are respectively depicted in this table. And consequently y1, y2, y3, y4 and y5 are followed. And at the last ycp and y hat I is depicted up to 7 levels. Optimization. Based on the equations obtained earlier, we conduct an experiment to optimize the terminal operation. Then the absolute throughput will be the target function. The maximum possible current volume of oil products in the tanks will be set as a constraint, and the oil product discharge rate will be set as a varying parameter. The model operating time of the terminal will be set to 1 year. We will set the generation of runs randomly. In addition, set the requirements that the volume in the tanks should not exceed the minimum allowable capacity now. So, as you can see here, the model is depicted, and we are going to show you a video which we describe how we did this. Turning into the conclusion, results, and implementations. This paper studies the effectiveness of the St. Petersburg oil terminal using the results of simulation software Anylogic. Quick estimation of the economic effort showed that implementation of the proposed technical solution can improve the economic efficiency of the transport system section, where St. Petersburg oil terminal is included by 10 to 12%. In this case, the cost of upgrading the system of pipelines and valves will be repaid in 4 to 5 years of its operation. Thank you very much. We are, as a team, Mikhail Afansiev, Dmitry Pervukhin, Dmitry Kutov, and Anna Somolenchuk. We are really pleased to gather all your information and your questions about this lecture. Please feel free to send us your questions. We are going to answer it as soon as possible. And we are ready for your feedback. Thank you very much.